So let me just first summarize what we've been looking at so far. As I said, we want to find solutions to equations of the following form, where Z is some sort of state vector. So it could be a vector in Rn, it could be a function of t, it could be a function of x and t, or it could be a vector of functions of x and t. L is a linear operator, think of it as a matrix. N is a nonlinearity. Epsilon is a scalar parameter. And the whole point of perturbation theory is to consider solutions that are series in epsilons, so that you turn this nonlinear problem into a sequence of linear problems. So this is the order 1 equation, and the order epsilon equation is L Z1 is minus n of Z0. We'll usually take this function n to be such that n of 0 is 0. To get a non-trivial solution to this problem, we want L to have a non-trivial null space. In the language of matrices, that just means determinant of L should be 0. In the language of operators, it just means there's a 0 eigenvalue, or more broadly, 0 is in the spectrum of the operator L. Okay? Since we have a non-trivial null space, you can't solve this equation for Z1 uniquely. But moreover, you can't solve this equation for Z1 unless n of Z is in the right range. So from the Fredholm alternative, we demand n of Z0 to be perpendicular to all y such that L adjoint y is 0. Right? So this is a requirement from the Fredholm alternative just to allow for the existence of solutions. And so this condition is usually where these reduced models appear. So the condition that the right-hand side be perpendicular to all y in the null space of the adjoint leads to conditions for unknown parameters at the level of the first-order problem. So since the first-order problem, so if you recall, Z0 can be any alpha v where LV is 0. Alpha is arbitrary. Alpha is a scalar that just scales your 0 eigenvector. The boxed equation is nothing but an equation for alpha. Right? And if the original problem was algebraic, then this is an algebraic expression for alpha. If the original problem was an ODE, this is an ODE for alpha. If the original problem was a PDE, this is a PDE for alpha. Okay? But this is the broad framework that I want to sort of keep in mind. Okay, so that's what we'll always do. So let's go over here. Last time, I considered I called it a function y, but I'll call it a function u for today's lecture. I considered an equation of the following form. So this was an ODE, and I had a parameter epsilon here. And I sort of did this perturbation calculation and ended up with an equation of the form 3 by 2 psi squared psi. And I think I have an I here. where psi is basically this alpha parameter that I had last time. Okay? I'm changing up notation just because I will be considering PDEs today. So today is the first lecture where I'll actually be true to the title of the series of lectures. Nonlinear PDEs is where we're going to start here. So last time I had something of the following form. And so today I'm going to consider a PDE of the following form. So it's got like a wave operator, and then a linear term u, and then the nonlinearity u cubed. So you can imagine last time I had exactly this. I've sort of trivially extended it into a PDE by adding some spatial dependence. And my goal is to show that this implies wait. Technically, it implies that. Where omega will turn out to be the dispersion relation. I'll explain all the terms soon enough. But my goal is to really sort of show you how spatial dependence gives something that we already saw, plus a new term introducing some spatial dependence. Just to be precise, these will be cap x's and cap t's. So they will be slow times and slow space variables. Just as previously we had a slow time, a new time at the order of epsilon squared t, I'll get an epsilon squared t, but I'll also get an epsilon x for the ride. Right, so there's an epsilon little x, which is what this capital X will turn out. So the goal is to start here and sort of arrive at these type of problems. So this expression is exactly what our boxed equation will turn into. So our boxed equation will give rise to this expression. Okay? And so we need to solve this for psi. Last time it was easy when it was an ODE because I could do this trick and show you that actually absolute value psi squared was a constant. That won't be the case here. So this is a legitimate PDE, and that's where I'll stop. This is a very nice PDE. We know a lot of details about this. And I'll speak to those details towards the end of the lecture about what we know and what we can say. All right, so the goal is to go from here to here. First things first, let's write it in our generic form of a linear operator Right, so now we have it in the form of linear operator plus some small parameter times nonlinearity equals 0. So Q is the original field U, P is the time derivative of Q, as you can see by reading the first line. Right, so Qt is minus P, Qt equals P, right? Okay, so that means my linear operator is nothing but ddt plus 0, negative 1, 1 minus dx squared, 0. And I want to know, does this linear operator have a non-trivial null space? Because the whole goal is to set up a perturbation scheme. And so my first goal is to find out whether I even have a non-trivial null space. Okay? Now you'll recall when I did the ODE problem, when this wasn't there, I said my overall goal is to find periodic solutions. So I'll still say the same thing. I want to find periodic solutions. But these are not periodic only in T. They will be periodic in X as well. And I'll see once again that just as before the period in T changes, the period in X will also have to change accordingly. Okay? All right, so I'm interested in periodic solutions. Right, So that's the goal. So this is my operator L. How do we solve constant coefficient differential equations? We always assume a form of an exponential and turn it into an algebraic problem. Right? So I'll assume, so this is the discussion of the null space of L. So assume QP looks like AB e to the ikx minus I omega t. Right? So k is any real number. So effectively, if I pick a k, I'm looking at functions that are 2 pi over k periodic. Okay? So if I plug this into, so substitute into L QP 0, 0, we end up with 0, -1, 1 plus k squared, 0, AB, I omega, AB. You just put that in, everyone gets an exponential, throw away the exponential, and so you end up with an eigenvalue problem for this matrix. I omega is the eigenvalue of this matrix. AB is the associated eigenvector. All right? So it's not too hard to show then that the eigenvalues are plus or minus I square root of 1 plus k squared. Just look at that matrix and figure out what its eigenvalues are, and then equate. You'll get 2 possible choices, so that's why I get the plus or minus. And the associated eigenvectors are 1 minus I omega of k, 1 I omega of k, where I'm making the choice now, so I'll define, where will I do this? Let's just do this here, big equals. Omega of k is the positive root. So I'll define omega to be that, and I get the plus and the minus associated, okay? So if you basically have to plug in the positive square root here for the 2 roots. You can compare this to the case of the ODE by setting k equals 0. So when k is 0, you are dealing with spatially things that are constants. So the derivative will go away, and then compare with what we saw last time, which is our eigenvalues were plus or minus I, and then our eigenvectors were 1 plus or minus I as well. So it's entirely consistent with what I did last time. It's just the trivial generalization with respect to PDEs. All right. So that's for this operator. So all of this implies QP can equal alpha e to the ikx minus I omega of kt 1 minus I omega of k plus complex conjugate plus beta e to the ikx minus I omega of kt plus 1 I omega of k plus complex conjugate. Again, I'm using the notation that complex conjugate just refers to the thing immediately preceding it. So alpha and beta are complex numbers, and this is my most general solution to the problem of finding the null space. Okay, alpha and beta, completely arbitrary, and you shouldn't be too surprised. Last time also we got e to the it and e to the minus it. I still have that. And now I just have a spatial dependence as well. And my frequency in time is sort of dependent on my wave number in space. Okay? So the goal will really be, we pick a k that tells us what our spatial period is, and then from omega, that tells us what our temporal period is. And then we will look at the operator L acting on functions which have that spatial period and that temporal period. Right? So we'll want L to act on functions with spatial period 2 pi by k and temporal period 2 pi by omega of k. Okay? Let's play a game. You pick any spatial period, you pick any temporal period. Well, let's say you pick the temporal period consistent with the spatial period. The real question is, does this uniquely specify k? How many k's can satisfy the same spatial period? All right? Or rather, how many k's can satisfy this combination? Now, since this function is actually one-to-one, there's only one k that works. Omega equals square root 1 plus k squared is a one-to-one function. Just plot the graph and you can see that it's completely invertible. So there's only, so telling me what spatial period is and then constructing the associated temporal period only gives me one wave number k. Okay? Suppose instead we had a different dispersion relation. Omega equal k cubed. Okay? In that case, this idea wouldn't work because k equals 0, the constant period, constant functions, will satisfy every period. Okay, so I would like to distinguish between the cases when omega of 0 is 0 and when omega of 0 is non-zero. The temporal period will always separate the different k's. The real confusion is whether k equals 0 matters or not, or to put it in a different set of words, whether the zero mode plays a role. K equals 0, the mean mode. That all depends on whether your dispersion relation touches the origin. In this case, the dispersion relation does not touch the origin, and so the mean mode will not be an issue. There's an example that I do for KDV in the notes where the dispersion relation is k cubed and the mean mode matters. And the analysis is slightly more subtle. So let's just distinguish those two cases. That's why I'm doing, even though this looks like a second order PDE, like why are you doing that as a more fundamental example? Well, that's actually because the real thing that you need to worry about is, does the dispersion relation touch the origin? Is omega of 0, 0? And the easier case is when omega is bounded away from the origin. Okay? All right, so for this problem, we can uniquely fix k by specifying the periods. So specifying the periods in a more mathematical way is to say I specify a specific class of a specific function space. By specifying the periods, I know exactly it's only those functions that'll leak in. I don't have to worry about having new functions creep in, new function spaces creep in, as would be the case for the KDV example, which is in the notes, the one after this. Okay? K minus k would give the same omega, that's true. So let's just normalize to positive k's. That's almost like a discrete symmetry, and I'm not too worried about that. I mean, it's almost like flipping x to minus x, and you can see your original problem has that symmetry as well. But that's almost like I could just quotient by that. I could say pick positive k's. I mean, k to minus k will just mirror something. And yes, that's a degeneracy, but it's not a degeneracy by introducing a new class of functions. It's the same function, just flipped. Okay. Similarly, omega to minus omega, you might say, that's another one. But let's just assume things that are moving forward rather than backward. That's the only difference. All right. So with this, I have classified what I mean by the null space. So this is the null space of L. Let's go to the adjoint. L dagger. So with k fixed, we define an inner product let's say z, which way do I do it? Z tilde z, where z is qp, z tilde is q tilde p tilde. And I'll define z tilde z to be integral 0 to 2 pi by omega of k, 2 pi by k, q tilde q plus p tilde p dx dt. Right? So I'm looking at the space of functions which are 2 pi by k, 2 pi by omega periodic, and I'm going to define the inner product as the following form. So this is just the Euclidean inner product and then integrate it over. Just like I did for the ODE case, but now I have two variables, so I'll integrate over both variables, x and t. With this, the adjoint, so L dagger such that, which way do I do it? Z tilde LZ should be L dagger Z tilde Z. Once again, this is really an issue of integration by parts. So you pick you basically put this L inside the inner product and then pass the time derivative acting on the original variables to the time derivative acting on the tilde variables. And that just means what you need to do is integration by parts. So originally you will have a dq dt. You want to pass that on to a dq tilde dt. So you'll get a minus sign when you do the integration by parts. We've got periodic boundary conditions, so the boundary term doesn't matter. With that, I can write down L dagger to be minus d dt, 0, minus 1, 1 minus dx squared, 0. So it'll look like the transpose of the matrix. Note, I've got a dx squared, which becomes a dx squared when you do integration by parts. So that's why that doesn't change signs, but it acts on the other term now, so they switch across the off diagonal. All right, so that's L tilde, L dagger. And L dagger has the null space e to the ikx plus I omega of kt, I omega of k negative 1 plus complex conjugate, e to the ikx minus I omega of kt minus I omega of k 1 plus complex conjugate. Sorry. Yeah, it's just that. Both of them become minus, so I forgot the minus overall. Okay? So how do I get that? In exactly the same way that I got the null space of L. Plug in the ansatz, find out what the eigenvalues and the eigenvectors are. You should not be surprised that the eigenvalues are exactly the same thing, because it's just the transpose of the original matrix. So omegas are exactly the same thing. the eigenvectors change. Right? They sort of switch their roles. So this is the null space of L dagger. And so we need the things in the box are the pieces of information we need to start the perturbation series. Right? At at the first order, order 1, we're going to know what the null space of L is. At the next order, we're going to want to know what should I multiply by to enforce the Fredholm alternative. Okay? All right. So with that, let's actually start our perturbation series. So let's start the perturbation series to be QP, to be Q0, P0, plus epsilon Q1, P1, plus epsilon squared Q2, P2. Any questions so far? Because I'm actually interested in real-valued solutions to this problem. And once again, I'm doing complex functions just so that I can compute cubes lazily. And I can multiply exponentials, and I know when I'll get a periodic function and when I won't. E to the I theta times e to the minus I theta is a constant, which will give me a contribution, whereas e to the I theta times e to the I m theta, averaged over the period, will give me 0. Whereas I don't have to worry about trig identities because I forgot them, and I don't have Wikipedia right now. Right? Any other questions? Come on, there's an easy question that someone should be asking. Yeah, that's a good question. It's a very good question. So initially, if you recall, I didn't have an epsilon. I just wrote the equation. And I played my usual trick, which is to say, let's scale u. So if I didn't have an epsilon, and I set u to epsilon u, I'd have an epsilon cubed, epsilon, epsilon, epsilon. So then I'll cancel one epsilon to get an epsilon squared. So if I scale things by epsilon, the natural number to see here is an epsilon squared. You could then just redefine epsilon. Like, look, epsilon squared is the only number I see. Let's just call that to be epsilon. But notice, even though I took an epsilon squared there, I took an epsilon expansion. Okay? The honest answer to the question, why did I take an epsilon when there was an epsilon squared in the problem, is because I know what I'm doing. And I know in the next step, I really would like to have an epsilon. But suppose you didn't know what you were doing, right? Well, when you don't know what you're doing, go back to a problem where you did know what you were doing, which is to say, go back to the ODE problem. Now, in the ODE problem, if you recall carefully, I didn't have an epsilon squared, although I should have had an epsilon squared. I just called that an epsilon. If I had introduced an epsilon at that stage, what would have happened? I would have had an order epsilon equation, which would have had a time derivative of the parameter with respect to that slow time epsilon. But it wouldn't have balanced the epsilon squared in the problem, because that's an epsilon squared, and I just scaled time by epsilon t. So it would have been on its own. So it would be a d alpha d time equals 0. So it's like, oh, it doesn't depend on that time then. So go to the next order, take an epsilon squared to balance whatever you have. PDE is slightly different, because if you had a slow time epsilon t, you're allowed to have a slow space epsilon x and still have some non-trivial balance arise. You don't need this just yet. I'll do the calculation, but I'm sort of giving you the heads up as to why I wanted a slow time, because I'm allowed to have an equally slow space such that they balance one another, and then I'll go ahead further. Since in the ODE case I didn't have a space, the balance would have just been the time derivative equals 0. And that's to say it doesn't depend on that time. We'll see precisely this calculation. That's a good point to bring up, which is for PDEs, always allow yourself more freedom, because things will always get more difficult, so give yourself as much freedom as possible. Okay? Any other questions? I haven't answered exactly your question, but you'll see in the next step precisely where this is going. And sort of to give you a heads up, I wrote down up till this term, which is to say I will go up to this order, and I'll apply the Fredholm alternative 2 times. Okay? It shouldn't be too surprising, because to actually get the nonlinearity to appear, I need to go up to epsilon squared. So if I actually want an interesting nonlinear problem, I need to take the expansion up to epsilon squared. But along the way, the order epsilon problem itself will give me something non-trivial. Okay? Any other questions? Good? All right, then, let's get to it. So, the order 1 problem is L, Q naught, P naught is 0, 0. And so then this says I will take Q naught, P naught to be alpha e to the ikx minus I omega of k t 1 minus I omega of k plus complex conjugate. Again, notice my null space consists of 2 different types, and I'm picking one, the alpha. Okay? I could have done the entire calculation by picking beta, and I'll get the complex conjugate or something very similar, but in terms of the beta variable as opposed to the alpha variable. Same thing I did for the ODE case. I had 2 choices. I picked one. You can also do both. We can talk about that later. Fundamentally, you'll still end up with the same kind of problem. The coupling is not so much of an issue. All right, so the order 1 problem is this. What is the order epsilon problem? Order epsilon problem, let's just stop there. So clearly, when I expand to order epsilon, the nonlinearity doesn't matter. This is an order epsilon squared. Don't care about that. So I'm just going to have this L operator act on 1, 1, which will give me an order epsilon. But, as always, that which was a constant make now a function. So we assume alpha is a function of epsilon x and epsilon t. Okay? So that means when the time derivative acts on this entire combination, it can act on this exponential, but that won't give me an epsilon. So that's the previous order. Or the time derivative can act over here, which will give me an epsilon. So if I put it to the other side, I get minus d alpha d capital T e to the ikx minus I omega of k little t 1 minus I omega of k plus complex conjugate. Capital T is epsilon little t. Right? I'll get that term for sure. Now, if you go back and look at this operator, you've got 2 x derivatives to take. Right? The matrix has to act on the lower order term. The lower order term times these constants, zeros and ones, is not going to give me anything at order epsilon. This derivative can. I'm supposed to take two x derivatives. What am I taking two x derivatives of? This combination, alpha times the exponential. Two x derivatives on the exponential is not going to give me any epsilons. That was the previous order. Two x derivatives on the alpha will give me epsilon squared, not what I'm interested in. One derivative on alpha, one derivative on the exponential will give me an epsilon. And then I can do one derivative on the exponential and one derivative on the alpha, because you can do it two ways. It's just the binomial theorem, basically. Which is to say, I will end up with 2ik alpha cap x e to the ikx minus I omega of k t 0, 1 plus complex conjugate, where cap x is epsilon little x. I get the vector 0, 1 because the only contribution from this matrix is coming from this x squared. Not from the 1 here, not from the 0, not from the minus 1, not from the 0. So when you actually work it all out, you'll only get 0, 1 vector, not the eigenvector. Okay? Tedious, but I hope obvious once I tell you what the answer is. Are we all good with this so far? Yeah? So, what do we have? We have precisely this condition, a non-invertible operator acting on something with a right-hand side. So the right-hand side had better be in the right space, which is to say this should be perpendicular to these guys. Right? Question? No. So all of this junk has to be perpendicular to both of these guys. Okay? Now, what are we going to do? We're going to multiply by one of those elements and integrate over the short period in x and the short period in time. So 2 pi over k and 2 pi over omega of k. For the purposes of integration, we will also assume any function of slow variables is a constant. So it will come out. So I'm really focused on looking at these exponentials. And I want to know which exponentials are going to cause me trouble. And I can already see it because e to the ikx minus I omega kt, 1 minus I omega, is a solution to the linear problem. It's in the null space. But it's on the other side of the equation. So there's no way that q1, p1 can have any component in the direction of that null vector multiply by L and still come outside, because the minute L acts on that null vector, it goes to 0. So this is not a vector I'd like to see on the right-hand side. There's no way I can get it. Put another way, how many times have you seen the phenomenon of resonance in a second-order linear constant coefficient ODE? When the right-hand side vector is in the null space, so y double prime plus y equals sine of t. You can't have sine of t on the other side because the solution now looks like d sine of t. And so it grows in time. So similarly, I don't want this vector, this function vector combination, I don't want it there. I want it to go away. What about this guy? He's got the right exponential, he's got the wrong vector. But this vector 0, 1 must have a component in one of these two vectors. Because these two vectors are a basis for the two-dimensional vectors, and 0, 1 must have a component in one of them, at least. And so once again, this entire right-hand side is an issue. That's all I'm trying to claim. So what we're going to do is multiply by this exponential times this vector, or its complex conjugate. This exponential times that vector, or its complex conjugate, to try and knock out those terms. Okay? If I were to multiply this e to the ikx minus I omega kt times, let's say, e to the ikx plus I omega kt, the omegas will cancel, but I'll get e to the 2 ikx, which I will integrate over a period, which will go to 0. So that's fine. So this expression, whatever it is perpendicular to this first combination. Similarly, what about this guy? Well, it's exactly the same function. So I'll get e to the 2 ikx minus 2 I omega kt, and I'll integrate over the period. That'll go out to 0, because it's a periodic function integrated over its period. Now let's go to the complex conjugates. The complex conjugate of this guy will have a minus here and a minus here. So the e to the ikx will cancel, and I'll get e to the minus 2 I omega kt, which I will integrate over a period, which will be 0. What about the complex conjugate over here? Well, this will be the exact opposite of this. It will be a minus here and a plus there, which will cancel both of them. That's the one I have to worry about, because that'll average to 1 when I take the average. So the complex conjugate guy here has to be multiplied by this part and integrated, and you'll get the d alpha dt out, plus some constants that depend on omega. Likewise, what about this? It's going to be the same thing, because it has the same exponential. Right? You might ask, what about the complex conjugates in that equation? They'll get multiplied by this guy. Right? So it'll lead to almost exactly the same condition. Again, details in the notes. I don't want to do it. I just want to show you the logic, which is you see the exponential, you want to see the adjoint exponential that will cancel this, and then you pick up the coefficients. So when you multiply this entire expression by the complex conjugate of this guy and integrate over, where's my integral? Integrate over this period, you will end up with the Fredholm alternative condition. So let's just go over here. Applying the Fredholm alternative condition leads to omega of k d alpha d tau dt plus k d alpha d cap x should be 0. You shouldn't be surprised that you ended up with a scalar condition, because the condition comes from an inner product. So this scalar condition is basically something times a vector that I wanted to be 0. And so to make it 0, I make the scalar up front 0. Okay, so you multiply that entire expression by the complex conjugate of this, which is to say we multiply the right-hand side by e to the minus ikx plus I omega of kt minus I omega 1, and then integrate 0 to 2 pi by omega, 0 to 2 pi by k. And you set it to 0. Right? And so you end up with some condition which is precisely this. This is what the left-hand side turns into. I can write this as d alpha d tau dt plus k by omega of k d alpha d cap x, which is a relatively easy equation to solve. Remember, as far as, k and omega are constants. We fixed k, and hence omega is fixed. And so this is just a simple advection equation. So what then this says is alpha should be some function psi of x minus k by omega k t. Any function psi. Right? Any function psi. You give me a function psi, and I can, this combination satisfies this equation. Which function psi? Well, to determine the arbitrariness at this order, you need to go to the next order. And the goal will be to show that the psi must be chosen such that that's actually true. On a slower time scale, not epsilon t, but epsilon squared t. I must have this C is the profile variable. Okay? So a couple of comments. First of all, just at this stage, look at what's happened. We said pick an initial condition that looks like a single Fourier mode with an amplitude that's almost constant. Then that amplitude satisfies this equation, and then that means that amplitude translates with whatever this profile is. Whatever this profile is, it changes on a slow time scale and a slow space scale. So just to give an idea of what the picture looks like. So the picture so far is e to the ikx and I omega t. So this is some 2 pi by k. It's some wave that looks like this. Zoom out a little bit, and you see that the amplitude of this wave needs to be modulated by some function, whichever function you want to choose. So for instance, so this is the order 1 solution. The order 2 solution so I'm not drawing this to scale, for sure. The order epsilon solution looks like this, where I've chosen some Gaussian type of profile. Psi could be an initial condition that looks like a Gaussian, in which case I'll get this wave packet type behavior. Honestly speaking, you can choose any function you want at this stage. We really don't know how that profile evolves. What I do know is that this fast wave oscillates at the phase velocity, omega over k, but this dotted wave translates, so the dotted stuff translates at k over omega of k. Right? Because that's the speed at which the psi profile changes. So this whole thing, the amplitude modulation moves at one speed. This high frequency bit moves at a different speed. The high frequency bit is basically moving at what you would call the phase speed, omega by k. It's not too hard to show that k by omega happens to be omega prime of k, which you may know as the group speed. So the profile translates at the group speed, and there's this high frequency oscillation that's moving at the phase speed. Okay? So we already know that whatever our solution is, it ought to look something like this. Physically speaking, what you're doing is causing an excitation at one particular Fourier mode and letting the system evolve. And if you wait long enough, which is to say on the timescale epsilon little t, if you zoom out enough, which is to say on the space scale epsilon little x, there's going to be a modulation of the profile. It can't just be a flat wave moving forever. It has to change its shape. And it'll change its shape in some fashion, but however it changes, that shape will translate at some speed. Okay? Questions about this? Yeah. That doesn't have to happen every time. That doesn't have to happen every time. Yeah, yeah, that doesn't have to happen every time. It might be related to the fact that I'm doing perturbation theory on Hamiltonian systems. But in principle, I can do perturbation theory on dissipative systems. And then what you will usually see is a monotonic quantity. Something should decay or something should be controlled. But the fact that there's always this sort of conservation law need not be true. That said, people exploit the fact that there is a conservation law. So if it turns out to be the case that you have a conservation law, brilliant, use it. So I want to say no, but I'm going to do the example, and it will have a conservation law. So I'll be completely undermined by my position. This thing has an infinite number of conserved quantities. So, I mean, I couldn't be more wrong. But I want to still say that that's not what the statement that at every order, for every problem, you will see this, that seems like too general a statement. But all examples I'll do will have that. There was a question? Yeah. Yes. In practice, the question is, how do you know which epsilons to pick? Largely, that is a combination of practice. It's a combination of talking to an experimentalist. It's a combination of sort of building up some intuition as to what you want to do. It is certainly true that you could pick any power epsilon you want. And suppose you did an epsilon to the 1/2. Certainly, you'll still get this. This will still be true. So then you'll go to the next order, epsilon. You will get something more complicated in that more x derivatives will appear, but it'll still be linear in that this is an epsilon squared, so this still won't appear. And you'll proceed till you hit the epsilon squared. Towards the end of this lecture, let me come to how you should pick epsilon from a strictly mathematical point of view, which is to say, how do you pick epsilon when you know absolutely nothing? From a physical standpoint, epsilon usually means something or corresponds to something in an experiment, in which case you pick the epsilon to explain the experiment. From a mathematical point of view, many options are open, and I'll say something about what each choice effectively means. Okay? But in practice, yeah, do lots and lots of problems and sort of learn along the way. Any other questions or comments? All good? Right, brilliant. So, what have we got? We have resolved this, and now let's move on to order epsilon squared. Right, so, oh, actually, not yet, not yet. Go back to order epsilon. Making this assumption doesn't turn the right-hand side to 0. It just makes sure the right-hand side is in the right space. Okay, it doesn't turn it to 0. So if we make this assumption and put it into the right-hand side, so d alpha dt and d alpha dx are related to this function psi, what you end up with is the following. L q1 p1 to be, what is it? Omega prime of k d psi d xi. Remember, xi is this traveling coordinate. E to the ikx minus I omega of k t 1 I omega plus complex conjugate. So the entire right-hand side chunk sort of simplifies into the following expression, where automatically the stuff on the right-hand side satisfies the Fredholm alternative criterion by construction. We look for solutions Q1, P1 to be e to the ikx minus I omega t AB, because I have exponential of that form. So let me just do something like undetermined coefficients, plug in the exponential I see, and try to solve. When you do that, you end up with, well, let's say plus complex conjugate. This gives rise to minus I omega minus 1 plus k squared minus I omega AB plus complex conjugate should be omega prime psych c 1 I omega plus complex conjugate. So now, once again, we're reduced to a linear system. I need to solve for AB. Recall that this matrix has a null space. Right? So when I invert it, I can always add something in the null space. But I can also have a particular solution. So if you just read the top line, you end up with that. And then this implies Q1, P1 should be e to the ikx minus I omega of kt, A 1 minus I omega plus complex conjugate minus omega prime of k psych c e to the ikx minus I omega t 0, 1 plus complex conjugate. Where this guy is arbitrary. Not surprising, since that arbitrary thing is multiplying the eigenvector of the original problem. Right? So I don't know what this is, and this is like a particular solution I have. At this stage, I can choose the A however I want. Okay? I can choose the A to be 0. I can choose the A to be any number I want. If I stop here, I'm good to go. If I want to go up further, I need to make an intelligent choice of an A. And it turns out the intelligent choice is really dictated by that the other vector that you have, this vector along 0, 1. If you proceed to the next order, you'll see lots of vectors along the direction 0, 1. So you would prefer not to have this other vector, 1 minus I omega. Every time you have a question, what should I do? Go to the next order. That's where things get decided. Arbitrariness at one order is pinned down at the next order. So A is arbitrary. I'll actually go to the next order, and I'll see lots of vectors along the direction 0, 1. Shouldn't be too surprising. Look at the form of your nonlinearity. It's actually along the vector 0, 1. So when the nonlinearity appears, you really want things aligned in the direction of 0, 1 vector so that you can apply the Fredholm alternative in an easy way. Mathematically speaking, you can pick A you want. And then you let the Fredholm alternative sort of tell you what's the most appropriate A. And I'm just telling you up ahead that the most appropriate A is set A to 0. Setting A to 0 doesn't mean the full answer is perpendicular to the null space, because that guy has a component along the null space. He's not perpendicular to any of the null space vectors. He's in their range. So setting A to 0 is not setting the solution orthogonal to the null space. It's just making a more intelligent choice. dictated by going to the next order. Okay? So, looking ahead, we'll set a to 0 in this equation. Right, so I'll sort of knock out that term. So, what does that mean? Just to summarize what we have so far. Story so far. QP equals psi c e to the ikx minus I omega of kt 1 minus I omega plus complex conjugate minus epsilon psi c omega prime of k e to the ikx minus I omega of kt 0, 1 plus complex conjugate plus epsilon squared q2 p2. So this is what my solution so far looks like. It looks like a single exponential times a traveling wave psi, and then I have another frequency at the same spatial and temporal period with a minus omega prime psi d psi dc. Yes? It is. You're saying, oh, why do I have this exponential here, right? It is. It is perpendicular to the adjoint. By construction, because this was the condition to make it perpendicular to the adjoint. And I said alpha to be psi. And so work out the calculation and see that it is actually perpendicular to the adjoint. Now, of course, I want to go to the next order. So that means that which was a constant must now depend on space and time. So what are my constants? Well, I'll say the profile remains invariant for this equation. So whatever psi you pick, it's the same thing, it just translates. That's the invariance I want to break. It's a profile that doesn't change in time. Okay, so let's make it a profile that does change in time, but changes slowly at another time scale. So my interpretation of that which was a constant has now been abstracted. What do I mean by that which was a constant? Oh, the profile was a constant, so it now must change in time. Before we go ahead, let's just understand that suppose psi is a 2 pi periodic function. In terms of little x, it's like 2 pi by epsilon periodic, because cap x has got an epsilon. So automatically you've seen that the spatial period has changed. So psi is a periodic function on a much longer time scale. Because of the structure, it's also time periodic with the same epsilon factor. But now I'm saying, let it now evolve on an even further time scale. Okay? So I'm going to say epsilon squared t, which I will call tau. So I want to know, how does this profile itself change? Okay? So we take that ugly ansatz, throw it into our equation, and now look for terms of order epsilon squared. The time derivative can act on the exponential, won't give me an epsilon. It can act on an alpha, will give me an epsilon. Or it can act on psi, which will give me an epsilon squared. So if I take a time derivative of psi with respect to tau, I'll get an epsilon squared. So this time derivative will give me a dd tau of this profile psi. What about over here? The 0 minus 1, 0 will only give me an epsilon squared if it acts on a number times epsilon squared. So it must act on the second order term. The x derivative, well, I have to see taking x derivative of different combinations. If I take two x derivatives of psi, I'll get an epsilon squared, because psi depends on the profile variable xi, and xi looks like an epsilon x. Remember, xi looks like epsilon x minus omega prime of k t. So if we go back to this expression, taking two x derivatives of this guy will give me an epsilon squared. I've already got an epsilon squared here. I've already got an epsilon. So I should take only one x derivative here. And I should take no x derivatives here. Or rather, I should take x derivatives of exponentials. Right, that's what it really says. Okay, yes? Why not a slow space scale? One could introduce a slow space scale. If you did that, well, certainly you won't get this equation. Once again, it goes to your previous question, how do you pick if it's either epsilon or epsilon squared? You're just asking the spatial version of that question now. And I will tell you the same answer, which is to say, practice, listen to someone else, know what you're doing. Or sort of, as I said, wait for the final answer when you don't know what you're doing to see what this epsilon could mean. In principle, you're allowed to do that. You'll just get more and more complicated / different equations. Okay? All right, so I'll keep that picture because I like that picture. The order epsilon squared equation is going to turn out to look like minus e to the, let me just call this theta, because I'm getting lazy, 0, 3 psi squared psi, which is coming from the nonlinearity, plus complex conjugate, minus e to the 3 theta, 0 psi cubed, plus complex conjugate, minus e to the theta, d psi, d tau, 1 minus I omega, plus 1 minus omega prime squared, psi xi xi, 0 minus 1, plus complex conjugate. So you can see that this nonlinear term gave me a 0, 1 type of eigenvector, type of vector. Here I've got a 0, 1 type of vector. There I've got a 0, 1 type of vector. So that's sort of what told me that I should have set a to 0 at the previous order to make sure that my answer is, my ansatz itself is in the direction of 0, 1. Okay? So once again, apply Fredholm alternative. Note, the trouble terms are this e to the theta and e to the theta. Those are the trouble terms. E to the 3 theta times any element e to the theta or e to the minus theta is perfectly fine. It's going to give me at least an e to the 2 theta, which if I average, I get 0. The trouble terms are these guys when they get multiplied by e to the minus theta. So the contribution of this thing in the square bracket and the contribution of that thing should all add up to 0. So once again, we will multiply by this term, the complex conjugate, which is e to the minus theta, times that associated vector. Take the inner product, do the integral, pull out everything that depends on slow variables outside the integral. And then you end up with a condition that something should equal 0, a scalar condition. And the scalar condition turns out to be this. Right? So you'll get a contribution from the psi tau term, you'll get a contribution from the psi square psi term, and you'll get a contribution from the psi xi xi term. So that's what I get. Now you might say, hang on a second, you wrote this minus omega double prime. How do you know that? Well, magically, it turns out for omega of k equals square root 1 plus k squared, omega double prime of k times omega of k is 1 minus omega prime of k squared. And I have an omega of k here. So this is again something that you can check. And so now what we end up is the Fredholm alternative says the profile psi must change on a slower time scale according to this equation. So you give me an initial condition for this profile, and I know that this, whatever this Gaussian is, has to start changing its shape slowly. Right? Do you have a question? So the main point I want to sort of get at is at this level, it basically tells me, well, okay, so suppose I have this function psi, then I can sort of enforce this condition and find out what Q2 and P2 are, and so then I have my solution up to order epsilon cubed. Okay? Where you need to tell me what the initial condition is. And the initial condition really looks like some high frequency wave times a slow modulation. That's all you need to tell me, and then I will tell you that that slow modulation changes in time according to this PDE, such that the total solution looks like this. Okay? So to answer the question that's been repeatedly asked, how do you pick epsilon? Your initial condition. The slow modulation you define in terms of the initial condition. So if you picked a slow initial condition that depended on a parameter epsilon to the 1/2, what is that epsilon to the 1/2? With respect to this number. So by slow modulation, you mean an initial condition that's really smooth and slowly changing on some spatial scale. So if that spatial scale on which it's changing is of order epsilon, when the small parameter is of order epsilon squared, then this is a good solution. Well, morally. If, on the other hand, you made it change on a different time scale or a different space scale root epsilon, then this is not a good solution. You need to find the equation that evolves on the root epsilon timescale to get an approximate. So it's really, what are you aiming for? And what you're aiming for is really based on how you perturbed the initial system. So you're looking at an initial system that had a high frequency oscillation, and then you want to modulate this. So maybe you have an experimental setup where there's a high frequency wave, and maybe the experimental apparatus tries to trap this wave in some region. How big is the region of trapping compared to the wavelength of the wave that you're trying to trap? Then it'll tell you how to pick epsilon. So if you want to introduce new space scales, you need a reason to, and one reason to is external conditions. So maybe this is actually a problem in some bounded region. That bounded region will, at some point, manifest boundary condition influences onto your problem. How far is the boundary from what you're interested in? How does that length scale compare to epsilon? Like rather non-dimensional length scale, how does it compare to epsilon? So that's sort of how you would choose. So morally, what are we really doing? We're trying to answer the question of the evolution of the system in a sort of constructive, getting our hands dirty sort of way. And the only way we know how to do this is to have a separation of length scales where we say, okay, something happens at some length scale, and then I can sort of put that to a side and ask what's going to happen at a longer length scale, and I'll put that to a side, and I can ask what's going to happen on a longer time scale. And all that depends on the balances you're interested in. So for instance, suppose you didn't even start off with an initial condition with a high frequency wave. Well, then don't even bother doing this analysis. If you started off the whole base problem with a completely different solution, which was very slowly evolving, then you should do the analysis accordingly. Ideally, your linear problem should have a constant as a solution. If it's only changing slowly on a long length scale and not a high frequency length scale, then omega of k should be 0 for some k. And k should be 0 is a valid solution to your problem. But you can see in this case, if you just, for the linear problem, if you set it to a constant, then the only solution is 0. Because if you set it to a constant, all derivatives go away, and you just get u equals 0. So there is no non-trivial constant that you can use. If your problem had derivatives on all terms, then it says that you're allowed to have one solution that just looks barely like a constant and then slowly changes on that some longer time scale. So this is sort of what I'm trying to imply, that there's this interplay between the things that are allowed by the linear operator and the nonlinearity that sort of picks up whatever is allowed by the linear operator and mixes things up. It introduces new frequencies. The solution to the second order problem, whatever it is, will have a particular solution e to the 3 theta. So whatever it is, I know I'm going to get a e to the 3 theta here. So I get high frequencies. But I also get slow modulations of the amplitude. And in this case, I get two kinds of modulations. I get the modulation of translation, and I get a modulation of some new phenomenology dictated by this PDE, which we may as well give it a name, nonlinear Schrödinger equation. Yes? Yeah, so it comes back to the question he asked, why did I not introduce a new space scale? And the reason I didn't introduce a new space scale is the question of what on earth does epsilon mean? And what epsilon means really is asking, which question are you trying to solve? The question I'm trying to solve is sort of answering the, I'm telling you which question I'm trying to solve at the end of the lecture, right? So the question I'm trying to solve is, there is a high frequency wave that's being modulated by some perturbation on some length scale. And that length scale is of order epsilon when the nonlinearity is epsilon squared. Now, if I had a new space scale, that if my initial condition had two space scales at the slow level, an epsilon and a root epsilon, then I would have had to construct a different kind of an approximation. My approximation is guided by the problem I'm trying to solve. The problem I'm trying to solve is guided by the dynamics question that you're trying to answer, which is, you start off with an initial condition, you want to know the evolution. So then the question is, what's the initial condition? Describe qualitatively the length scales involved in the initial condition. My choices have dictated that I must have solved a problem with only a length scale of epsilon, and not epsilon squared little x. Okay? That's the main issue. So if you picked an initial condition that was changing on epsilon x, epsilon squared x, epsilon cube x, then yes, this is a bad approximation. If you are considering only that, then this is a good approximation. So unfortunately, these are not things that people tend to mention, largely because in the literature, when we construct these things, we don't prove anything. And it's only when you start doing the proof you realize you can't prove that that's a good approximation for any initial condition. It's only a good approximation for a certain class of initial conditions. Which class? The ones that only change on epsilon little x, not the ones that change on epsilon squared little x. So you have to prepare your system. Interestingly enough, that's the same word an experimentalist would use. I have to prepare my system to show a certain dynamics. So I have to prepare my initial condition, mathematically speaking, to show that that's the right approximation. Or if I had a different initial condition, I should have constructed the length scales accordingly. Okay. All right, so the question is, you started off with a system that was non-integrable, but you ended up with a modulation equation for Schrodinger equation, the second order problem, which is an integrable thing. So first of all, to get everyone on the same page, this is an example of an integrable Hamiltonian system. What that means is a lot of things, but just for the sake of conversation, let's say, as I mentioned to Divya, that this is a system with an infinite number of conserved quantities. So, for instance, it's not too hard to show that integral psi squared, integral with respect to xi variable, is a conserved quantity. There's a Hamiltonian associated with this. There's, as I said, an infinite number of conserved quantities. So, certainly, I got this out of a non-integrable model. So it turns out that equation is not integrable. Just take that for me. As Manas mentioned, many times you end up at nonlinear Schrodinger equation. So let me just emphasize the point that one of the reasons why I knew this had to be omega double prime is because that's what it always is. So when you pick a balance such that there is a high-speed oscillation modulated by a function such that it changes on little x times epsilon space scale and epsilon squared little t time scale, one inevitably gets the nonlinear Schrodinger equation. That's a generic feature. So start off with a system close to a Fourier mode and ask how should the Fourier mode change. It will translate in space at the group speed. It will modulate in space according to nonlinear Schrodinger. That's a generic statement. Now the question Manas is asking is that something to worry about? Of course, I'm not going to answer that question directly, so I'm going to sort of answer it indirectly. The fact that a linear problem is solved by exponentials, no one seems to ask, is that something I should be worried about? I mean, all linear constant coefficient problems are solved by exponentials. No one seems to ask that question. I mean, is there anyone who wants to ask the question, why did you start off with exponentials? You want to ask that question? The answer is, because it works. Right? That's the real answer, because it works. Now, of course, exponentials are very special functions. They form a basis of integrable functions on the line. They are the kernel for the Fourier transform operator. They have all these magical properties. So special functions, which are solutions to special ODEs, have special properties. So let's abstract that answer and say there exist special PDEs that generically arise under certain generic conditions which have special properties and are good approximations for generic systems. So in that sense, I would look at this the same way you look at the second order differential equation, y double prime plus y equals 0. As far as I'm concerned, this is a special equation which has special properties, whose special solutions are great approximations to a whole bunch of systems. Because, of course, this is a PDE, the null space of this is spanned by, I mean, it's a very large, infinite dimensional null space, and it can exhibit all kinds of peculiarities. But that's just the price of doing business with PDEs as opposed to ODEs. So just as Bessel function is a special function, Chebyshev polynomials are special functions, parabolic cylinder functions are special, integrable PDEs are special. And where do integrable PDEs come about? When there's a specific balance. As was asked repeatedly, if I had taken an initial condition that evolved on multiple space scales, I won't get an integrable PDE. So one reason why I chose this is because I'm a mathematician, I like beautiful structure, I wanted this PDE, so I knew what to choose. So when there is a special kind of balance is when you get an integrable model. So why did I get the integrable model? Because I chose a special balance. Suppose you did the experiment in a finite system, finite size system, and then you had to include finite size system effects. Integrability is typically broken. Why? Because there's forcing at the boundaries, and now it's a different type of problem. So we get these special PDEs because we made special choices, and there exist special PDEs that cover a whole variety of generic cases. Yeah, so that's the answer that I can give. It's a philosophical answer, but yeah. Yeah. Correct. Yes. Yes. Typically, so the only word I yes. 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 Do the so yes. So a model being non-integrable does not imply there are no conserved quantities. In fact, that's a Hamiltonian system. So, and I believe an analog of momentum defined in terms of the vector u ut should also be conserved. So there are, and if there's a physical meaning to it, probably there's a mass, which is probably like a trivial conserved quantity. So usually you get 3 if it's a problem from physics. So those 3 will obviously be still conserved. An interesting question is, the Hamiltonian momentum and mass of the original problem in U, what does it correspond to for this problem? And you can sort of follow the mapping and sort of try to define the associate. So write down the Hamiltonian, do the change of variables, and try to get a reduced Hamiltonian and see if it's the same Hamiltonian you get here. Usually when you're lucky, that works out in a nice way. And so then you can start doing Hamiltonian perturbation theory. So you can perturb the Hamiltonian structure or the Hamiltonian itself and play games at that level rather than the way I've done it, which is playing PDE perturbation theory. Nonetheless, the Fredholm alternative condition will almost always appear at some point or the other because that's all linearizations will lead to that. So there may be conserved quantities. You are choosing special balances such that there are more conserved quantities, and it's a nice evolution described by a nice PDE. Want to work with messy PDEs? Feel free to go ahead and make some other assumption. I mean, as you've probably seen, if you pick initial conditions such that they're not really satisfying this ansatz, the match between your simulation and your model prediction from the reduced model are different. Which is to say, the error changes at a faster time scale. Right? Any other questions? Yeah, right at the back. Sorry, 1 second, just behind you. Yes. Sorry, can you speak up a little bit? So the universal model typically arises when you pick certain classes of initial conditions. The universal model arises usually when you don't want some boundary effect or something to break the universality, if you will. So effectively, I've chosen initial conditions that don't feel any boundary, no other length scales except the inherent length scales of the problem. Otherwise, I wouldn't say that there's a universality to it. This is just a mechanistic procedure that you can apply as you want based on the choices of the initial condition that you want to work with. So if you want to work with an initial condition that has different kind of interesting spatial structure, have at it. Does that answer your question? Can you speak up a little bit? Nonlinear Schrodinger because I made the choice that there was no little epsilon xi. If I had chosen psi to modulate on little epsilon xi as well, I won't get nonlinear Schrodinger. Not at this level. I'll get some other equation. Eventually, I may get nonlinear Schrodinger at a different length scale. Maybe. Over here, I made a choice that there's a modulation at epsilon squared little t. I didn't say I'll modulate the xi variable, this thing, this Greek letter, right? I did not choose that. Right? That would be an epsilon squared little x. I did not make that choice. You may ask, why? One reason is I want nonlinear Schrodinger. And if I make that choice, I won't get nonlinear Schrodinger. Yeah. Yeah. Typically, no. So I want to answer that question in a slightly different way, but I'll first take your question. Yes, that's right, because ODEs are easier. For this one, yeah, I think what you can do is actually set up, so expand in a Fourier basis in space and time, okay, a Cartesian product of those things, and then set up a Newton iteration scheme for the PDE here. And you can then show from bifurcation theory that there exist small amplitude periodic solutions. So basically, set this to 0. There exist periodic solutions, which are precisely these guys, these exponentials. Show that the operator is invertible up to a null space. Set up your projections appropriately so that you can solve this iteratively. That is, invert the linear operator onto this, and then do a fixed point argument and show that that fixed point converges using implicit function theorem, Banach fixed point argument, on the space of functions which are periodic with some period and some time period, and then show that such time. So for small amplitude solutions, I'm fairly sure you can set up a Newton iteration scheme and show that there is periodic solutions. Yeah. Yeah, that's right. That's right. That's right. Correct. 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 It should be no surprise. Yes. Yes. So basically, your initial condition effectively encodes what you mean by spatial scales. So if your initial condition is, something that looks like this modulation is a spatial scale that you have introduced into the problem. How big is this modulation compared to, in non-dimensional terms, this number? Defines what you mean by epsilon. Okay? Now, of course, notice the solution to this problem is not necessarily going to be perfectly time periodic. I mean, it will be some time period, and it'll modulate, but that's not answering the full question that you started off by saying, does this problem have time periodic solutions? Because that'll be a fixed time period, and it will be exactly periodic with that time period. Whereas here, what's going on is we're constructing a sequence of approximations. We're saying it's periodic 2 pi by omega, 2 pi by k. Okay, not really. The spatial scale has changed, and the temporal changes scale. Okay, not really. It's changing slightly differently. So you could try to ask for space periodic, time periodic solutions to this problem. And then you'll realize, well, I can't get exactly the period, and maybe my initial condition for that PDE should start changing. But this is exactly what a Newton iteration scheme would try to do. Try to get an approximation, try to make the approximation better by allowing some change, and set up a sequence of approximations. So there are two slightly different questions here. I started off with the goal of trying to find periodic solutions, and I have constructed almost periodic or a close approximation to a periodic problem. That's one possibility. Another possibility is typically what Manas works on, which is you want to solve the initial value problem to this PDE, and then you try to solve this by constructing approximations. So solve the initial value problem to that. Both of these questions are related. It's a question of really what you meant by the linear operator. What's the space of functions you're dealing with? Does the adjoint have the same, like what's the inner product? What are you actually trying to solve for? The two problems are very, very closely related. I try to work with only the periodic case because things are a little more mathematically better defined. Trying to solve the initial value problem, usually what you do is you just say, let me take the entire solution expression, plug it into that equation, and try to see how bad is the residual. And then that's the theorem you can prove, that the residual is small when the initial condition to this PDE is suitably chosen, blah, 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 blah. Okay, so it's a question of what you're trying to do. So there's sort of like two different problems that we're looking at. I'm trying to construct periodic solutions. He's trying to look at the initial value problem. And yeah, it depends on those things, the interpretation. Yeah. Why U cubed? Ah, okay, okay. Do you have a? Yes. 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 Okay. Yes. Well, no. There are two things. It's the linear operator that also plays a role. That also plays a role. Yeah. Yeah. So clearly, if I don't have the U cubed, I'm not going to get the psi cubed. So that's one reason. The other reason is actually the cubic nonlinearity is nice in one particular way, in that if you start off with e to the theta and cube it, you get e to the theta, e to the 3 theta. If I had quadratic, I would get e to the theta and e to the 0. And I don't want to deal with the 0 mode yet. And so to answer what happens to the 0 mode, read the notes for KDV. Because KDV is a UT plus U triple X plus UUX. So it has a quadratic nonlinearity, so it has a possibility of generating the mean mode. Generally speaking, that's a harder problem when you generate the mean mode, especially if the linear operator omega of k is such that omega of 0 equals 0. Because then both of them are in the null space. The 0 mode is always in the null space, and the k, and so fixing periods doesn't uniquely identify a wave. So you have to deal with a legitimately two-dimensional null space. So the real reason I chose cubic is because I don't want to deal with quadratic nonlinearities, which are actually more annoying. Even though you may think that they are more generic, that a generic nonlinearity will have all of them, so you should have dealt with the quadratic first. Why didn't you? Yeah, that's why, because I don't want to deal with that. Was there another question? Is universal. In what sense? Yeah. So let's sort of So suppose you start with a nonlinear PDE. and I mean something like a weakly nonlinear, Lz plus epsilon nz, such, and so then this gives me a dispersion relation. Omega of k for the linear problem. And then you ask the question, what happens to initial conditions of the form psi, possibly depending on slow variables, e to the I kx minus I omega of k t. So suppose that's the question you ask. I start with a single Fourier mode, I slowly modulate it, and I want to know how should the slow modulation change, which is to say, which PDE should the slow modulation satisfy. So we separate this into some cases. So case 1, omega double prime of k is non-zero for some k. What that basically means is omega double prime of k is not identically zero. So generically that means omega double prime of k is a function of k. So usually omegas are analytic functions of k, so this just means it's some generic function of k. In this case, you get psi satisfying nonlinear Schrodinger, generically. I mean, there are some degenerate cases, but generically this is what happens. So it's in this sense universal, that when you have a dispersion relation that's what I'll call non-trivial, then psi, the slow modulation, generically satisfies NLS. Yes? Sorry, you're going to have to speak loud. Precisely. Well, I don't have omega double prime. Omega double prime is not zero. Omega, in this case, so omega double prime of k is not equal to zero for some k, at least. I mean, omega double prime in this case is just k by omega, and it's not zero. Not identically zero. So if it's not identically zero, then it must be non-zero for some k. So the opposite of this is omega double prime of k is identically zero. What does that mean? It must be a linear function of k. So let's split this into two possibilities. So it looks like a k. In this case, psi satisfies KdV, Korteweg de Vries. Okay? And then the other possibility the opposite of that. Omega is identically zero. I don't want to give this guy a generic name, but I gave a lecture as part of the Bay of Bengal air-sea interaction program that was recorded at ICTS, and I derived what's called quasi-geostrophic theory, and that's an example of this case. This is omega prime. Yeah, this is omega prime. Yeah, because suppose the opposite of this, so this is for some k, right? So then the opposite of that is omega prime of k is zero for all k. Omega is zero. Not omega prime, not omega is literally zero, which is to say there's a steady state to your problem. This tells you the time dependence of the exponential. So this is true for all k. So there are special solutions which are steady, and they don't distinguish the k. They're steady for all k. And that's precisely what happens in atmospheric science when you have the Coriolis term included for the Euler equations for fluid dynamics, and you have a three-branched dispersion relation. Two of them look like this case. One of them looks like that case. So an example of this is quasi-geostrophic theory. And technically also Navier-Stokes. So these are the base problems where this phenomenology is seen. Also shallow water equations. Really, you get quasi-geostrophy from shallow water. Right? So those are like sort of the three possibilities that you can get. If generically omega prime is non-zero, then you almost always get NLS for this type of an ansatz. So you basically ask what's going to happen. You can ask, well, what about this cubic nonlinearity business? You want the cubic nonlinearity if your system is scalar. The potential theory-based water wave problem has a quadratic nonlinearity, but when you do the slow modulation of an exponential, you still get nonlinear Schrodinger. So the generic feature is really that slow modulation of an exponential will fall into three possible categories: nonlinear Schrodinger, KdV, complicated stuff. So it's in that sense a universal model. All right, any other questions? Yeah, so I'm actually saying that there is a set of solutions to the linear problem that are steady. They have no time dependence. There's a non-trivial steady solution to the problem. No, I'm literally saying set the time derivative to 0 for the linear problem. Is there a non-trivial solution? That's all. So for instance, in this case, suppose you set the time derivative to 0. Then the solution to the linear problem looks like u equals u double x, whose solutions are exponentials in space, e to the x and e to the minus x. They're not periodic. So then there are no non-trivial, periodic, steady solutions to this problem. If, on the other hand, instead of a minus u double x, I had a plus u double x, my problem is elliptic. But then I would have a steady solution, sine x and cosine x. So in the shallow water equation, there are steady solutions that you can find that are non-trivial. There are such exponentials which have an omega that is 0. So they're just an exponential, doesn't change in time. That's what I mean by omega equals 0. Yeah? Any other questions? All right, if not, we'll break for lunch, and I'll see you guys tomorrow.